Okay, hello everyone in a new video. So we have reached part 2 of chapter 4, which is the chapter of resistors for grade 10 students. So we have reached section 4 eventually, and the title of this section is given by the electric power. So given any electric component D, independent of the nature of this electric component, the electric power across a component D is given by, so suppose this being traversed by a current I and its applied voltage is U, then the electric power by definition is given by P is equal to U multiplied by I. So let me say where P is the electric power consumed its SI unit is given by capital W, which stands for watts. U is the voltage. Its SI unit is V, which stands for volts. And I is the current, and its SI unit is A, which stands for amperes. Okay, and now let me directly get into section number 5, which is electric power across a resistor. So we know that the electric power in general is given by P is equal to U multiplied by I. So this is the first form. Now suppose that we are interested in applying Ohm's law, which is given by U is equal to R multiplied by I. This is given by Ohm's law. Now replacing this expression of U and the expression of I here, we get that P is equal to, so this is the first form, is equal to R multiplied by I, which is equal to R multiplied by I multiplied by I, which is equal to Ri square. Then P is equal to Ri square is the second form. Now starting back again from P is equal to U multiplied by I, and U is equal to Ri, which is Ohm's law, which means that I is equal to U divided by R. Now replacing the expression of I here, we get that P is equal to U multiplied by U divided by R. Then in this case P is equal to U multiplied by U divided by R, which is equal to U squared divided by R. So in this case P is equal to U squared divided by R. And so let me make them more clear. So I think this is clear. So this is the third form. Okay. So now in this case, we have three different forms for electric power. P is equal to U times I. This is the first form. The second form is given by P is equal to Ri square. And the third form is given by P is equal to U square over R. And the important note is that forms 2 and 3 only applies if the component is a pure resistor, So whenever they ask me about the electric power, we must think of these three formulas. And in the case of a resistor, so we can use this or this. Now recall that in grade 9 we used to use these formulas, but before we use them we should prove them. Now in grade 10 no need to prove these forms, we can directly use them. So now after we have determined the expression of the electric power across a resistor, so let me start with section number 6, which is the electric energy. So the energy in general is given by E is equal to P multiplied by T, where E is the energy, its SI unit is given by J for joules, P is the power, its SI unit is W, which stands for watts, and T is time, and its SI unit is S, which stands for seconds. Okay. Now the following important note that we should consider: if P is electric in nature, which means P is the electric power, then the energy E is equal to P multiplied by T is electric, in which P is equal to U multiplied by I. Okay, and let me specify a convenient unit of energy which is given by kilowatt hour. That is used domestic installations or install that is used in domestic installations. So let me here make it clear that this is kilowatt hour. Or when calculating the electric bill, but remember that the SI unit of energy is joules and not kilowatt hour. So in grade 9 we have used kilowatt hour as a convenient unit of energy whenever we are calculating energy over a long period of time. But whenever we are interested, or domestic installation, but whenever we are interested in small electric circuit, one may consider the unit of energy which is given by joules. Okay, so this we have seen in grade 9. So the formulas that we only should consider is that P is equal to U multiplied by I, P is equal to U square over R, or P is equal to Ri square for a resistor. Also this holds for a resistor, and that E is equal to P multiplied by T. And the unit of power is watt, and the unit of energy is joules, and the SI unit of time is second. All of these are the SI. Okay, so now without further ado, let's solve the following exercise. They are telling me consider UPN is equal to 12 volts, as we have mentioned several times, so it's convenient to label the voltage here. R1 is equal to 5 ohms, R2 is equal to 1 ohms, R3 is equal to 3 ohms, R4 is equal to 4 ohms. So number 1, they are telling me to determine the resistance of the resistor equivalent to these 4 resistors. So we will start by the 2 resistors that are directly, so they are straightforward, the grouping is straightforward. So notice that in this case R3 and R1 are not in parallel because this terminal is not connected back here. The same thing goes for R2 and R3. However, notice that R1 and R2 are in series. Then the equivalent resistance is given by R12 is equal to R1 plus R2, which is equal to 5 plus 1, which is equal to 6 ohms. Then R12 is equal to 6 ohms. And whenever we calculate an equivalent resistance, we need to represent it in a new electric circuit. Now in this exercise, it will be obvious why it is convenient to represent the equivalent resistance in a new electric circuit. So this is the battery. Here we have 2 resistors. This is the point P. This is A, I prime, and I double prime. So this is B, this is C, and here let me write that R12 is equal to 6 ohms. This is R12, this is 12 volts, this is the point N, this is R4, and this is R3. Okay, so we need also to label everything on every circuit. Now notice that in this case it's obvious that R12 and R3 are in parallel. When they tell us determine the equivalent resistance, we need to replace all of these 4 resistors by a single resistor. Now we need to say that R12 and R4 are in parallel. So the equivalent resistance is given by 1 over R24, which is equal to 1 over R12 plus 1 over R4, which is equal to 1 over 6, okay, plus 1 over R4, which is 4. Then here we need to consider that we are adding two fractions. Then we must consider the common denominator than the simplest form of the fraction, and eventually it's given by 5 over 12. So 1 over R124 is equal to 5 over 12, which means that R124, if you consider the reciprocal or the crisscross, is given by 12 over 5 ohms. And as usual, we will represent this. So let me say that this is the first circuit. The order of the circuit is also extremely important. The second circuit is given by, the third circuit this is R124. Here it's not R124, but it's rather R123, because also I have noticed this because the value is not reasonable. So this is 1 over 3, which is equal to 1 over 2, which means that 1 over R24 is equal to 1 over 1 R23, which means that R123 is given by 2 ohms. So this is 1 R23, and this is R4. This is the point B, this is the point C, this is the point A. Notice that in this case I prime and I double prime vanish. Let me label here a current I, which is the main current. So this is the main current I, this is the main current I, this is the main current I because this is a main branch. Okay, this is a main current I, the main current I. I wanted also to stress on the fact that if you have a component and on the first terminal is being traversed by a current I, then for sure on the other terminal is being traversed by a current I. Okay, so the current I is the same for both terminals of any electric component. Now it's left, so this is the electric circuit 3. This is the point P, this is the point N, and this is UPN is equal to 12 volts. Now the final equivalent resistance that we want to consider is the one in series between R12 and R3. So let me say that R123 and R4 are in series. Now we can drop down the numbering notation, and we can say that R equivalent is equal to R123 plus R4, which is equal to 2 plus 4 equal to 6 ohms. Then R equivalent, always the final resistance, we name it to be R equivalent. And the final electric circuit is given by this. Then eventually the point B will disappear. This is the point C, traversed by current I, and this is the point P, this is the point N, and UPN is equal to 12 volts. Now each question they ask us, we have 4 different circuits to refer to, and here we have that the equivalent resistance R equivalent is equal to 6 ohms. Then we are done with number 1. Now they are telling me to deduce the intensity of the current sent by the generator, and deduce, it means that we need to use the previous part. The previous part is related to the final equivalent resistance, which is this circuit. So notice that this is R equivalent of value 6 ohms, and if UPN is equal to 12 volts, then the applied voltage here UAC is equal to 12 volts. No need to prove it because it's the only component present in this circuit. So let's say apply Ohm's law to R equivalent, which is given by U is equal to R multiplied by I. We are interested in determining the value of I, which is given by UAC over R equivalent, which is equal to 12 over 6, which is equal to 2 amperes. So the value of the main current I is equal to 2 amperes, and as we have mentioned previously, the trick in solving such type of exercises is to label the value of the current I 2 amperes over all electric circuits that we have determined. So this is 2 amperes, this is 2 amperes, this is 2 amperes, this is 2 amperes, and okay, so probably the first circuit, okay, and I here it is 2 amperes. Okay, now what I wanted to say is that if you want to use another time Ohm's law in the circuit, just for short, I will not mention any time, I will not mention any more Ohm's law, okay, because already I have mentioned this during the exercise. So because in this exercise I have mentioned for once apply Ohm's law, I will not mention it again. Now in this case we are done with figure 4. So here let me place in blue that we have used figure 4. So whenever they ask us a question, probably we need to refer back, and we refer back in the reverse order from 3 to 2 to 1. Okay, so this is the trick, also another trick in solving exercises including resistances. So they are telling me we need to determine the voltage UAB and UBC. So we need to find a circuit that includes UAB and UBC. So the easiest one that one should think about is the circuit that comes directly before 4, which is a 3. Notice that in this case UAB can be directly calculated using Ohm's law. As I have mentioned, that no need to mention Ohm's law because we already mentioned once in the exercise. So the applied voltage across AB is given by the resistance R123 multiplied by the current I, which is equal to 2 multiplied by 2, which is equal to 4 volts. So UAB is equal to 4 volts. So let's write here that UAB is equal to 4 volts. Now think about it. What is the voltage that will be added to UAB to give us 12? It will be 8. But without thinking of the law of addition of voltages, UBC can be determined also using Ohm's law. So UBC is equal to R4. This is as a double check that our calculation is correct. Multiplied by I. The value of R4 is given by 4. So 4 multiplied by 2, which is the current traversing UBC, is equal to 8. So UBC is equal to 8 volts. So this is also UBC is equal to 8 volts. But the thing is that, as we have mentioned previously, whenever we determine a voltage, we need to represent it in other configurations. So this is UBC is equal to what? 8 volts. And now here let me place a blue mark on this electric circuit, which means that we have used this. Now it's left to use circuits 2 and 1 regarding voltages and current, okay? Not any other question. So now let me make some space. Now in number 4 they are telling me to calculate the power, and the power is given by P is equal to U multiply, and this is not governed by any law. Now delivered by the generator G, by the generator, so the generator we can refer to any electric circuit. So the generator have a voltage U, so P of the generator G, say for example, has a voltage UPN traversed by current I. The value of U is given by 12 and the value of the current is equal to 2, so this is 24. Since both U and I are expressed in the SI, so the value of P in the SI, which is watts. Then P of the generator G is equal to 24 watts. So here the generator is considered to be an electric component traversed by current I and having a voltage U is equal to 12 volts and the value of the current is equal to 2 amperes. So by definition its power is given by 12 multiplied by 2. Now in part B, so okay, why they are using these terms delivered and dissipated? Because the generator is the one that delivers a power and these resistors are the one that consumes power. For this reason we say dissipated. Now between A and B we are free to choose any electric circuit, so either 4, 3 or 2 or even 1, but notice that in case of this, the third configuration, we know the voltage between A and B and we know the traverse current, so directly P across A and B is equal to UAB multiplied by the current I, which is equal to the voltage UAB is 4 and the value of the current I is 2, which is equal to 8 watts, because everything is expressed in the SI. If U is expressed in the SI, which is volts, and I in the amperes, so the value of the power is volts times ampere, which is equal to watts. So PAB is equal to 8 watts. Now as for number 5, they are telling me calculate the energy dissipated by the circuit during 2 minutes of functioning. We know that the energy dissipated, which is the electric energy, is equal to P multiplied by T. But now here the energy can be calculated in two methods. It is the energy due to R1, R2, R3 plus R4, or we can simply calculate the energy of the generator, because these resistors are consuming energy directly from the generator. So it will be P of the generator because it is due to the electric circuit itself. So this is equal to what? P of the generator is equal to 24 watts and the time T is equal to 2 minutes. But we know that the SI unit of time is seconds, so 2 multiplied by 60, this is equal to 120 seconds, because we know that each minute contains 60 seconds. So E is equal to 24 multiplied by 120. Plugging this on the calculator, then it's given by 2880. Since this and this are expressed in the SI, so the value of E in the SI will be joules. Notice that I didn't determine the electric energy in kilowatt hour because they didn't mention anything about the unit of energy, so we must calculate it in the SI. Now they are telling us the terminals A and B are joined by a wire of negligible resistance. So since we have done a change in the electric circuit, everything that we have done will eventually change, except for the voltage of the battery will remain the same. So everything here will change. So they are telling me the two terminals A and B are joined by a wire of negligible resistance. So what we have done here is short circuiting, and whenever we do a short circuiting, all of this electric circuit can be ignored. So the electric circuit will look like this. So this is the point A, this is the point B, and this is R4. So this is P and this is N, and we have that UPN is equal to 12 volts. So whenever they tell us joined by a wire of negligible resistance, all of the components between the negligible resistance can be ignored and they can be simply considered as a connecting wire. They are telling me calculate the intensity of the new current sent by the generator. So suppose this is the current I4 sent by the generator, and I4 can be determined using Ohm's law because U is equal to R multiplied by I. No need to mention Ohm's law because we already mentioned during the exercise, so I is equal to U divided by R. And here, since this is 12 volt and this is the only electric component existing in the circuit, so it will carry an applied voltage 12 volt, the value of R4 is given by 4, which is equal to 3 amperes. So I4 is equal to 3 amperes. And this is reasonable. Why? Since we have removed some of the resistance, we know that the resistance and the current are inversely proportional. As R decreases, then the value of I will increase. So this is it for exercise number 2. Now let's move to the next exercise, which is exercise number 3. Now 5 resistors are connected to an ideal battery of potential difference 12 volts. Now what is meant by ideal will be left to the next chapter. So here we have that UPN is equal to 12 volts. Now we have the value of the resistances R1, R2, R3, R4 and R5. Number 1. Verify that the total resistance of this circuit is R equivalent is equal to 80 ohms. So we will start by the two resistors that their grouping is obvious, which is given by R2 and R3. Then R2 and R3 are in series. Then R23 is equal to R2 plus R3, which is equal to 50 plus 10, which is equal to 60 ohms. So R23 is equal to 60 ohms. Now, because we have determined a new equivalent resistance, we need to represent it in a new electric circuit. So this is the battery. This is R1, point A. This is R12. This is R4. This is R5. Let me give all the labelings: R1, R4, R23, R5, current I, points P, A, B, and N, currents I prime, I double prime, and a main current I traversing the main branch. Now notice that R23 and R4 are in parallel. So 1 over R234 1 over R23 plus 1 over R4, that is equal to 1 over 60, and here let me say that R23 is equal to 60 ohms, plus 1 over R4, 1 over 30. Now adding these two fractions on the calculator, which is equal to 1 over 20, we are considering the common denominator and the simplest form. Therefore 1 R234 is equal to 1 over 20, which means that R234 is equal to 20 ohms. And let's represent it in a new electric circuit. This is P, I. So this is N, this is B, this is A, and this is P. This is R1, this is R5, and this is R2, 3, 4. Now finally notice that all of these three resistors each has a common point with the next one, so all of them are said to be in series. So this complex circuit boils down to an equivalent resistance. They are telling me that the total resistance, so it must be replaced by a single resistance. So R1, R2, 3, 4, and R5 are in series. Then R equivalent equal to R1 plus R2, 3, 4 plus R5. Here let me say that R2, 3, 4 equal to 20 ohms. So the equivalent resistance is given by 60 plus 20 plus R5, which is 20 up here, which is equal to 80 ohms. Sorry, this will be 100. So why? Because let me see, no, okay, sorry, R1 is given by 40, so R1 by 40 plus 20 plus 20 is given by 80 ohms, so R equivalent is equal to 80 ohms, and it is convenient to represent this in a new electric circuit. Here we have that UPN is equal to 12 volts, I think. Okay. Now let me label the ordering of the circuits 1, 2, 3, and 4. And each question that we will be asked about, we need to refer to these 4 circuits. Now in number 2, they are telling me deduce the current I. So whenever the reason behind determining the equivalent resistance is to determine the current I. So for once in this exercise we will say apply Ohm's law, and by deduce it means that we need to use the previous circuit, which is the last one, the final one, which is R equivalent, includes R equivalent. Then U is equal to R multiplied by I, knowing that you are interested in determining the value of I. Then I is equal to U divided by R. Since this is the only component appears in the circuit, it will take the applied voltage of the battery, which is UPN, of equivalent resistance R equivalent, which is equal to 12, divided by the value of R equivalent, which is 80. Now 12 divided by 80 is equal to 0.15 amperes. Then I is equal to 0.15 amperes. Now after we have determined the value of I, we need to label this I in different electric circuits that we have considered. So 0.15 amperes, 0.15 amperes, 0.15 amperes, 0.15 amperes, 0.15 amperes. The same goes here. Okay. And let me make space above here. So for sure now, because we have determined current, they will ask me about voltage, then current, then voltage, then current, so on and so forth. So this is the logic. Let me also change the notation here. They are writing U, it should be they are writing V, and it should be U. So this is U, U, and U. And now in number 3. Then determine the voltages UPA, UAB, and UBN. So because we are done with the circuit, we will mark it by blue, which means that we will refer to number 3. So notice that in this case, we know the resistance R1, R234, R5, all of them traversed by respective current 0.15 amperes. Then we can determine using Ohm's law the voltage UPA, UAB, and UBN, and if we add them, they must sum up to 12 volts. So no need to mention Ohm's law because already it's being mentioned once in this exercise. So UPA is equal to R1 multiplied by I, which is equal to the value of R1 given by 40 multiplied by 0.15, which is equal to 6 volts. UAB is equal to R2 which are across the voltage A and B we have R234 multiplied by the current I. R234 is given by 20 multiplied by 0.15. This is equal to 3 volts. And finally UBN across the resistor R5 traversed by the current I is equal to, so the value of R5 is 20 multiplied by 0.15 and equal to 3 volts. And notice that in this case they sum up to 12 volts. So let me say that UPA equal to 6 volts, UAB is equal to 3 volts, and UBN is equal to 3 volts. And the same goes here, that we have that UAB is equal to 6 volts, UBN is equal to 3 volts, and UPA is equal to 6 volts. Sorry, UPA is equal to 6 volts, whereas this is equal to 3 volts. Okay, great. Now they are telling me deduce the powers PPA, PAB, and PBN, and they are telling me deduce, which means it's related to this, and we have determined the voltages and we know the currents. So let me say that PPA is equal to UPA across the component PA. We have the voltage 6 multiplied by the current, then 6 multiplied by 0.15, which is equal to 0.9. Both of these are expressed in the SI, which means that P will be expressed in the SI, which is watts. Now as for the power across A and B, which is the applied voltage UAB multiplied by the current I, the voltage UAB is 3 volts multiplied by 0.15, which is equal to 0.45 watts, and this is reasonable because it is the half of this. Now as for the power PBN, which is the voltage UBN multiplied by the current I, which is equal to, now the voltage UBN is 3 and having a current 0.15, so this is equal to 0.45 watts. Now notice the following: if you add these powers, they will add up to 1.8 watt. So this power is the power consumed by all of these electric components, which must be the power delivered by the generator to the circuit, which is simply 12 multiplied by 0.15. Now if we try this on the calculator, so this is exactly equal to 1.8 watts. Okay, so we are done with 1, 2, 3. Now as for part 4, okay, they are asking us verify that the total power dissipated by this circuit is equal to the power delivered by the battery. Now the power delivered by the battery is ppn, or the power of the generator, which is equal to upn multiplied by the current I, which is equal to 12, multiplied by 0.15, which is equal to 1.8 watts, as we have just discussed. Now, and at the same time, P total is equal to PPA plus PAB plus PBN, which is equal to 0.9 plus 0.45 plus 0.45, and it's equal to 1.8 watts. In this case, PPN is equal to P total, or PG is equal to P total, and in this case this is verified. We are done with part 4. Now in number 5, they are telling me to calculate I prime and I double prime. So we need to refer to the circuits in which I prime and I double prime appears. The easiest circuit is this one. Here we have I prime and I double prime. So I prime can be determined using Ohm's law. Why we cannot use the law of addition of currents? Because we don't know the value of I double prime. So this is two equations and one unknown. So I prime is given by U divided by R. It has an applied voltage given by 3 volts across the resistor R23, which is equal to 3 divided by R23, which is given by 60. Plugging this on the calculator, 3 divided by 60, this is equal to 0.05 amperes. Now as for I double prime, it is given by the voltage UAB across the resistor R4, the voltage UAB here is given by 3 divided by R4. The value of R4 is given by 30. Plugging this on the calculator, it's given by 0.1 amperes. And notice that if you add 0.05 with the 0.1, it's 0.15, which is the value of the main current, which means that the law of addition of current is verified. Now let me label here that this is 0.05 amperes and this is 0.1 amperes. So I double prime 0.05 amperes and I double prime is 0.1 amperes. And finally, they are telling me to determine the electric energy supplied by the circuit by the battery during 1 minute, supplied by the battery. So the electric energy by definition is given by E is equal to P multiplied by T. We are talking about the energy supplied by the battery, so we use PG, which is equal to 1.8. Now as for time, this is 1 minute, which is equal to 60 seconds. Then 1.8 multiplied by 60, this is equal to 108. Since both P and T are expressed in the SI, so the value of E will be in the SI, which is joules. Then the energy E is equal to 180 joules. And that's it for me in this video, guys. In the next part, we'll complete explanation and solve more exercises on this chapter.